This session, the overarching theme is marine contaminant transport and sensing. And we have a very interesting talk. There is a slightly an outlier in the talks, which is the last one. The last talk is from my former postdoc visiting scientist in Sensum and now assistant professor with tenure at the Belgian University, and he was one of the pictures which Andrew showed. So he's a success story of Sensum, and his talk is a little bit out of the line, even though we have a module for sediment transport in the model, but we don't use it. Okay, so the first talk is the history of marine paleoclimate and anthropogenic lead in the Singapore region, coral history and seawater sampling. And Professor Boyle is here to present the talk.
Okay, thank you, Paolo.
Thanks. Yeah.
And I've already pushed the wrong button. So. The which? Gripped it the wrong way, and there we go. We had it briefly. Okay, so I'm giving a retrospective of the work we've done here at Sensem over the last 7 years, and there are a few bits that we're still working on now that you won't see yet, and Gonzalo Carrasco will introduce that in the next talk a bit. But we've had a lot of people involved, and there are actually many others I'm not listing here because they're not involved with the work that I'm showing here today, but they're involved with the work that we're doing presently. Okay, so when I was first asked to possibly participate in Sensum, I looked around at things I knew about and could possibly find a research focus on. And I said, with Singapore, well, you know, what could I do that's relevant to Singapore? And so I thought, well, I work on coral reefs, as you'll see. And here we are in the middle of a lot of coral reefs, so it was an appropriate thought to think about that. So that's the starting point. And of course, Singapore is not only surrounded by many regions that have coral reefs, but it has many of its own. And there are people here that we've cooperated with who are studying corals, so it was a good collaborative point. Okay, so why study metals, isotopes, and paleoclimate in Singapore corals? First off, there are metals such as lead and cadmium that are toxic and at high levels hazardous to marine life and humans who eat those, the seafood. But there's a problem that it wasn't until the late 20th century that scientists developed the ways to measure trace metals in seawater. And so if you go out to Singapore Straits now and measure any trace metal, you have nothing to compare it to. We don't know what it was 100 or 200 years ago. So you're really just sort of left in this vacuum of not really knowing, has it gone up, has it gone down? You don't know anything. And so we can't use historical data. And as you'll see, annually banded corals do record past concentrations of metals in the ocean. And so we can establish the evolution over time. And basically, for this engineering-focused group like Sensum, think we're putting chemical sensors into a time machine. So we're putting sensors that go back 100 or 200 years and tell us what the concentration of metals in the ocean was at some previous time. Of course, we know climate is evolving, and it's done it naturally in the past, and now due to global warming. And so, again, there's some data on climate change, but you know, what was the salinity of the Singapore Straits 100 years ago? No one knows. There wasn't anyone here to measure it. So you have to find out some other way to learn that. And if you want to project things 100, 200, 300 years in the future, when you only have a few decades of data, you're on pretty shaky ground, no matter how good your model is. So we'll use the annually banded corals to get isotopic and geochemical records of climate conditions and metal histories. This is an X-ray photograph of a slab of a head of coral about this big might be 20 or 30 years old. So if you take that and make a flat slab of it and put it on a medical x-ray, you see these banding patterns. And what happens is that on an annual basis, depending on growth rates and other environmental conditions, at some points the corals make denser skeletons or less dense skeletons. They do tend to do this on an annual basis. And so like tree rings, you can count back year by year by year to get a history. So we have a good chronology, and then things are incorporated, isotopes and trace metals, into the coral reef skeleton, and then you use that as a way to get the history. So now normally you don't take something this big to do a paleoclimate record. You want something that's 50 or 200 years old. And so you go out and find, as best you can, some giant brain coral about this big, and then use hydraulic or pneumatic drill rig to get a core, and then you slab the core and do the x-ray. So this is what we're typically working with. And so Intan Nurhadi and Yanni Tanzil here in their best Charlie's Angels pose as they're out obtaining this coral core here, which is about 50 years long from Jong Island off of Singapore. And this is the basis of a large part of our work. I hired Intan because she was recommended to me by a colleague at Scripps Institute of Oceanography, and she had just finished this thesis work here looking at Central Tropical Pacific paleoclimate records. So using two paleoclimate indices, the O18, which is a function of the temperature and the salinity of the water, and then the strontium-calcium ratio, which is just a function of the temperature. And then, of course, you can take temperature and temperature plus salinity, subtract them to get a salinity signal. And she observed over these 50-year records here in the Central Tropical Pacific that some sites had increasing freshwater inputs and some didn't change much at all. And she looked at that in the context of upwelling in the climate. So she had the tools to do this paleoclimate work. She chose to go mainly here to the Western Pacific Warm Pool, Singapore over here. So we're seeing the Indonesian through flow coming through here from the Pacific into the Indian Ocean. Let's see, this is, okay. So this changes over the years, so over the course of a year. So in the southwest monsoon in July, the flow is mainly through the Makassar Strait here from the Pacific into the Indian. But then in the northeast monsoon in January, there's also a significant flow from the South China Sea into the Indian Ocean. And there's an island with corals called Natuna. And so she found a good coral there and created a record of the sea surface temperature and the sea surface salinity from those geochemical proxies. So here you can see here for temperature, the red is the data based on the strontium calcium measurements of the corals, and the gray is the best climatology that can be obtained. Obviously, it's not so much detail early on, but at least there are estimates of it, and you can see they agree pretty well, showing about, over this period of about 80 years, a 0.5 degree to 0.7 degrees rise in the sea surface temperature. And now, with the O18 measurements and the strontium measurements in the same sample, you can also look at the sea surface salinity and see that it had been getting fresher over time. Of course, if you get temperature and salinity, you also get density. And that's important because there's a correlation between the strength of the Indonesian through flow and the density of the surface water at Natuna in the South China Sea. So red is the Indonesian through flow, black is the density. And so now from this coral record, we have 80 years showing that the density has been decreasing, which would be pointing to a weaker Indonesian flow through over that 80-year period. And so we can then work together with Paula and other physical models to say, why should that happen? Does it make sense? Can we understand this? Okay, well, we don't yet, but we'll work on it. Okay, so now I'm going to move on to trace metals. You know, even though we've known for a half century after Claire Patterson's work that lead is harmful to humans, nonetheless, over and over and over again, we get examples of people ignoring that and doing themselves in with lead. One of the most recent one is the city of Flint, Michigan, that messed up their water treatment plant and led to very high levels of lead in the water and a lot of harm and economic destruction from this. So it's still a significant problem. It's not so much in the open environment. You're going to see that the concentrations are picomolar, 10 to the minus 12th molar, so very low concentrations, but the marine environment gives us the sense of how we have basically polluted the entire ocean with things like lead, and so it serves as a reminder that, you know, we can't just keep forgetting about this. So metals like lead are emitted by high temperature activities, and they go into the atmosphere, and then the atmosphere transports them on Jason Cohen's aerosols to remote regions of the planet. And in the broader Singapore region, you've got, of course, as you've seen, the Asian brown cloud pollution, local and regional sources, and so different regions are going to have different stories. And just as a quick example, this is what we saw in the region of the North Atlantic Ocean, which has had a large amount of leaded gasoline emitted by the United States and Europe, but it came in and then it went away. And so going to corals and then taking seawater samples for the last, from 1980 to 2000, you can see there's a buildup in the lead concentration due to industrialization, and then the big rise due to leaded gasoline consumption, and then the decrease to the phasing out. And because the lead sources are changing through time, you also have an evolution of the different lead isotopes, and that can tell you something about where the lead is coming from, and so it's a very useful tool that you'll see more of today. But if you go to different regions, you see a different story. So if you go to Rhode Island and look at the last 200 years, this is a history where a source of lead that was very common in the United States in 1850 led to this peak in the lead isotope ratio and then a fall. But then if you go to British Columbia, you see a completely different history. So you need to look at the regions, and they're all going to be different. So, you know, given the Asian industrialization, and we know there's going to be lead emissions. This is a NOAA simulation of the black carbon aerosols being distributed by the atmosphere. So we know there's going to be lead coming out of here and into the South China Sea and Singapore Straits and Indian Ocean. And so in a couple of papers, we used samples from the Japanese expedition to the Western Indian Ocean here, going from Arabian Sea down to close to Antarctica. In these figures, these are sections, depth sections, going from 0 to 5,000 meters in the vertical axis, and then 20 degrees north on the left and 70 degrees south on the right. And you can see here high lead levels in all the surface waters of the Indian Ocean due to that Asian industrialization. And that it also, as you can see here in this profile from this station here at 40 South, these characteristic Asian aerosols in this region of about 1.14 to 1.15, the lead 206 to 207 ratio, and then other ratios showing similar features here. So we do have this characteristic thing. And then going to the corals, we can then, Chagos Island, Central Indian Ocean, big rise in lead over the last 50 years because of the Asian industrialization. And then that 1.14 to 1.15 ratio in the corals because of the lead that was being used in that industrialization. But then a big anomaly appeared, and Andrew briefly alluded to this. If we look at the 50-year records from Jong Island in Singapore, we don't see that 1.14 to 1.1567 lead. Instead, we see something that's 1.18 to 1.20. And that's in contrast to what you see in Western Sumatra here and at Chagos Island in the Central Indian Ocean. So what's going on? Is this some local source to Singapore? Probably not. If you look at aerosols in Singapore, we collected on the building of CREATE and S16 for 2 years, and you can see here it's kind of in that 1.14 to 1.15 ratio here, and pretty constant, not constant, but always in that range. Whereas if you look at the seawater in the Singapore Straits, it's 1.2, just like we're seeing in the corals. Okay, to try to get a little bit more temporal history in this, we went to the McRitchie Reservoir and measured a sediment core for the lead. The reservoir is relatively pristine, as any of you have been out there walking around it know. Of course, there's a little bit of housing and stuff, but mainly not too much in the way of industry. And so it's going to basically be a trap that collects the aerosols from out of the atmosphere and leaves a history of what's been in the aerosols. So here now, in a sediment core that covers about 100 years, you go from the beginning of the reservoir in 1891, where you have this red soil, which has a lead isotope ratio that's just the natural ratio of this part of the Earth's crust, and very low concentrations of lead. And then from 1900 up until the mid-century, increasing. And then in the corals, you see that, and then finally the decrease as we phased out leaded gasoline. But again, the lead isotope ratios are all poised here in these low ratios that are characteristic of Singapore aerosols. So why does Singapore marine waters, corals, have this high ratio? Is someone from the United States coming out and dumping lead in Singapore Straits? Probably not. So that's the problem that was posed to us. And eventually we've figured out in a study looking at the interaction of natural particles containing natural lead with the industrial pollution that we took a sample from the Johor River estuary. Yes, okay. And we measured the lead and the lead isotope ratio in the dissolved lead and in the particulate lead. And then we took that bottle of water and added a spike of lead isotope ratio that was very different from what we saw in the natural sample. So we took that bottle from here, which is the initial dissolved lead isotope ratio, down to here by spiking it with this isotope ratio. And then over a period of a few hours to a month eventually, you see the ratio rose back towards the level here. And the basic premise of what's going on then is that there is a natural equilibrium between the dissolved lead in the water and that sticks to the surfaces of particles. And the particles coming down from the Johor River are mainly natural lead that's been weathered from the Earth's crust. So the minerals that lead are in are very unstable. They react, they dissolve, they stick to the surfaces of whatever particles are left behind. And so the particles that come down from the Johor River have a crustal ratio of lead 206 to 207. But then when it sees the industrial lead from the aerosol fall out, there's an exchange process according to this KD relationship, which relates the adsorbed particulate lead to the dissolved lead. It's basically the same formula a chemist uses in a chromatographic column, very common assumption. And so basically this experiment here is following that kind of behavior. We start off with initial lead composition on the particles, and we make the dissolved very different, and then over time there's an equilibration between the particles and the waters. So here we discovered something in Singapore waters we wouldn't have been able to see in North American waters because the crustal lead, the natural crustal lead, and the aerosol lead is about the same isotopic composition. Here, because they're so separated, it was very obvious that something was going on. Okay, other things, 170-year record of lead in a Vietnamese coral, and other things that are ongoing now. Gonzalo Carrasco will be showing you a few of these things in the next talk. We have started looking more into the variability of lead and lead isotopes and other trace metals around Singapore. and in the region. So we have samples from all of these places here around Malaysia and in Borneo. And so that's coming up, no data yet. And then thank the team members who contributed to this work, and it's been a very good time working here, and I'm glad I was able to work with all of you. Thanks.
Ed Boyle. So I'm going to take over the second part of the chair. Yeah. We do one question.
One question, there is 1 minute.
Exactly.
One quick question. Where would you say there is someone
Maybe I can ask a question, if nobody wants.
Fine, you go.
So can you elaborate on the technique used to measure these isotopes? How difficult is it to get these very tiny concentrations just right?
Well, there are very sensitive analytical instruments called multi-collector plasma mass spectrometers. They use a plasma that you introduce your sample to as a fine spray. It ionizes all of the lead, and then you go into a high vacuum system where a mass spectrometer separates these. Danfeng Wang here at NTU has one of these instruments. They're very sensitive, but the trick is how to process a seawater sample from the moment of collecting it to getting it to the instrument to make the measurement. The instrument works fine. You buy them, they work, but there's a lot of work and knowledge in learning how to get from picomolar levels in the environment to a sample that you can actually make the isotope ratio measurement by the plasma mass spectrometer.
Right. Good. So
There may be 5, 10 groups in the world that can do things like this.
Okay. Okay. Thank you very much again. We're going to continue with a talk from Gonzalo Carrasco. Sorry, Gonzalo Carrasco. And we are very happy that he's standing on stage. So, yeah, with that, applause. So, please go ahead.
Sure. Okay, so I'm going to tell you quickly about what has happened over the last 3 years here in my part of the operation in Singapore. I'm going to be talking about complexation and bioavailability and bioavailable concentrations of zinc and cadmium in Singapore coastal waters, the Malacca Straits, and the southern South China Sea. There's a long list of collaborators. Most of this work was done with the help of Yanni, Meng Li, Asani, Moritz, and a bunch of other people as well. So there's a lot of people to thank. Importantly, Ed just gave a talk, and you guys should go and take a look at the posters that Meng Li, Moritz, and Xiu Qin are setting up about work in mangroves, a large riverine project we have in Malaysia, and some of the lead story as well. But those are the collaborators, the laborators now over the last few months while I was in the hospital, were my very faithful students. Caroline, Jiawei, and Jui were doing quite a lot of work basically on their own while I was recovering. Okay, now let me go to a brief intro, which is most of you must have heard already a few times. Well, I'll try to go quick. We study trace metals because they're important for for enzymatic requirement to the cell. Here we have a cartoonized version of carbon, phosphorus, and nitrogen uptake, and they are mediated by enzymes that use these metals. Iron and zinc notice that zinc is used for the carbon and the phosphorus uptake. Cadmium is here and can replace, as well as cobalt, zinc. So we care about the bioavailability because of the total concentration, of the total dissolved concentration of metals. We need to know what are the fraction, what is the fraction that is actually going to make the biological effect. So we know that the pool of total dissolved metal can be broken between inorganic, free, and organic compounds, but in nature, largely this is dominated by these ligands, which basically means that the total dissolve is mostly as an organic complexes, which is mediated by the really strong binding strength with which this chelating agents chelate to the metals. The problem being that these two are the portions that are bioavailable. So if you're talking about a metal that has a nutritious role, you could be starving of something for biological purposes, even though you have a large concentration. Now, if it's a toxic element, it can be a good thing, right? Because most of it will not be bioavailable, and a small fraction only will be bioavailable. So we've been studying this under the common assumption, sort of the paradigm of these ligands being produced in surface waters and the vacuum, sort of in the open ocean. And my stay here in Singapore was basically to try to prove that was not the right assumption, that we should actually take a look at not only industrial sources of metals, but riverine matter as being important sources of humics. So basically, in my master's and my PhD, I did a lot of work in the Pacific and the Atlantic, and lately in my postdoc in MIT, I did work in the Middle East, and we basically found that the binding strength of the strongest of the ligands that binds to zinc, around 11 and a fraction, these are in log scales, basically for the Atlantic and the Pacific is what I found in some of these places that relate to water masses that come from distal sources of riverine material. And in my time in MIT, with Ed, we went to Kuwait and we did some work in the Tigris and the Euphrates River directly, and we found exactly the same strength of the binding agent, proving that the rivers, the riverine end member compares really well with distal riverine signatures. So the idea was then to try to see that in this region, which has so many rivers and so much organic matter coming from these. So over the last few years, we've been basically working pretty hard at setting up a trace metal clean lab at SMART. We did that with some funding we got from Sensam in 2015. And then in 2016, we sampled all over Singapore and a little bit of Malaysia, sampling for seawater, river water, and corals. And then we also did quite a lot of work with Janelle, trying to set up sites for harmful algal bloom sites around Singapore. In 2017, we have 3 projects that we are still working on. One of them related to the different monsoonal time of ligands and metals around the region at a different point in time. And then we also have one mangrove project that we sort of piloted last year. And then we are working on this coral project that I'll tell you a little bit more later, with the idea of basically being able to understand the ligands now and in the past through coral records. So we can actually look at the past and look into the future. Basically model ligand and metal bioavailability, how they control the metals, and then how that will change in future climate scenarios. The main questions then are, at the regional scale, we want to know if the ligands of humic origin come from rivers into the sea. How do these ligands change interseasonally? At a local and zonal scale, so for Singaporean interests, we want to know how do these local sources of ligands, which can be related to phytoplankton or seawater in general, traversing through the Singapore Straits, harmful algal blooms that can be found in the Johor Straits, or mangrove as sources of organic matter, how do these respond to metal sources, which are pretty diverse in the Singapore region, in the Singapore local scene. And at both scales, we want to figure out what is the primary regional regulator of bioavailability, how large is the regional trend versus the local influence of diverse factors, and what can we infer from humics recorded in corals about ligands through time, so that we can understand about that. And we can actually get an assessment about riverine organic matter controlling metal bioavailability in the past and in the present and in the future. So basically, we're trying to look at the same question from 4 different scales, but it's basically the same question. I mean, whether it is a regional study, a local study, a zonal study near a few meters up or down a mangrove, or a microscopic study, we're basically looking at the same question. So we chose Singapore because Singapore has a diversity of places to study all sorts of things. You can actually find very polluted from a trace metal perspective, right? I mean, shipyards and oil rig platforms in the urban areas, and also pretty pristine places, and also a lot of fish farms, a lot of industry towards the west. In the Malacca Straits, we did work in separate trips, looking at the Malacca Straits and the South China Sea. And we basically got this high-resolution sampling scheme done last year, which basically finished the day before I broke my leg. The Malacca Straits is a really interesting place in the South China Sea because we have everything between pretty riverine-influenced environments, relatively clean places, but also a whole lot of agricultural activities related to palm oil. So basically, I'm going to be talking about these four types of the directions of results: metal concentrations, bioavailability or non-bioavailability of the bioavailability and non-bioavailability distribution of metals, the seasonal changes, and the potential sources of trace metal contaminants from a biological perspective. First, to start to talk about trace metal sources. I will tell you briefly that there are natural sources that change through time. Here we have at Kusu Island some oscillation in terms of other elements, and in other stations around Singapore, you can see that there are some anthropogenic sources that are much larger than the natural sources. Ed mentioned a couple of things about lead sources, and if you want to know more about this, you should go and take a look at Meng Li's poster. In terms of the ligands, which is sort of the meat of the story of my presentation here. Now, basically the idea is this: on all of these places, we initially chose these 3 sites to take a look at the binding strength of the chelating agent to see if they do compare with the ligands that we were finding remotely. And we did find that the ligands here in the Malacca Straits at Port Dickson were basically in the same order of magnitude of binding strength. These are here in the narrowest section of the Malacca Straits. So the water basically narrows here all the way to the narrowest point, and then it opens up into the South China Sea in something that I refer to as a Malacca sort of funneling effect. Now, looking further at more samples, we did have some samples that I sort of cleaned up the data a little bit to try to figure out and get some trend. From all of these samples, trying to filter out samples that would be too influenced by other factors. So we got to a point where it would be more or less linear going up and down, getting into the highest point around the Malacca Straits and Port Dickson. Now, what we did over these last few months, what my students did was run a lot of the analysis for all of these other sites. Here we have Port Dickson here. They did a lot of the Malacca Straits work, and then they did a couple of extras on the South China Sea samples. And then they did also a whole lot of, this was the challenging part, doing a lot of these Rajang samples from around here, from one of the biggest rivers in Borneo. So what we found was basically that the same trend prevails with a little bit of noise, yes, but it basically goes up and then it goes down. And that, but more importantly, rivers are much larger source of ligands. So here in the Malacca Straits, there's a couple of small rivers, but then the larger rivers are the Pahang here and the Rajang and the Igan here. So we need to study some of those closer. If you want to hear about that, you should go take a look at Moritz's poster talking about the Rajang project. So again, if we filter out a little bit the data, we basically get a similar trend going up and down going up on the Malacca Straits and going down on the South China Sea. Same funneling effect. If you look at cadmium's a little bit more messy. I mean, we got some data initially, but then we started to get the high resolution data. It is a little messy. I mean, there's a lot of ups and downs. So we were confused. The river is not clear either. So in fact, we basically end up saying that the ranges are relatively large in the Malacca Straits section, The range is relatively smaller on the South China Sea section, and it's pretty variable, meaning that there are some ligands and there's some excess metal on the Rajang River. So we basically need to study much more the river systems. We found some seasonal changes as well. We studied this. We haven't done it on the Malacca Straits. We've done the seasonal changes only around Singapore. And what we found was that and on these 5 sites, and I will go over each one of the 5 sites pretty quickly, the range is huge. We go from 0 to 400 nanomolar zinc and all the way to 1 nanomolar cadmium. And there are some that are excess metals, some that are excess ligands. So it's a really confusing, apparently, place. But if we go one by one and separate each one of the stations, here we are at Kusu. Kusu sees only ligands for zinc and only excess cadmium, meaning that probably this could be sort of the natural scenario whereby cadmium is upwelled and changing through time through the monsoonal seasons, and zinc, the zinc ligands are changing also within a relatively narrow range between 3 and 5 nanomolar. We are actually continuing to try to do this, looking at organic matter coming from Sumatra peat in a project that we're working with Patrick Martin from NTU. If we look at other places, we found actually almost by accident. It was not the point to do this, but we found evidence of a logarithmic trend, decreasing concentrations of zinc and cadmium, which we think to us are related to land reclamation settling down. In a couple of other places in the West Coast, we found West Coast was an interesting place because West Coast is right here, right next to a big shipyard operation, and we found that there was excess of metals for both zinc and cadmium in 3 points in time, but at 1 point in time there was a lot of ligand for cadmium and also a lot of ligands for zinc, implying that this was a point where the environment was sort of responding to the environmental injury that this load of metals was meant. We actually do have a mangrove station report from 100 meters away from here that is discussed in Xiuqin's poster further down. If we go to a couple of other places, Kranji and Pungol were interesting places where we talk about fish feed, so basically fish farm operation, meaning a source of metals that I really wasn't counting on. I thought that this would be a source of organic matter, but it was a source of metals instead. So the question of bioavailability and bioaccumulation comes up. We're probably going to be working on that later on. Now the question about corals also, I'll try to be super brief about this. Ed introduced the idea of the coral bands. Here we can see them bioluminesce with UV light, and we can actually quantify the amount of humics that are accumulated in each year. And with this idea of humics, if we could quantify, we could get an idea about ligands, as the ligands and humic matter sort of relate. And more so, since Yanni has, this is from her 2017 paper, where she has a beautiful study of all the rivers around the Peninsula of Malaysia. The seasonality from river data and trying to compare it with what you find in luminescence in the corals. So, in a nutshell, what we wanted to do was we wanted to study in this region the influence of rivers on the marine environment. And yes, we have done that for the last few years. We are actually quite happy to see that rivers are important, and we need to figure out what biological agent or where do the ligands come from if they come from rivers. If there's any ligand being produced or brought into the system, what ligand is it, if it's a strong ligand or not, and then how is that going to affect the zinc bioavailability and the distribution of ligand of zinc between different pools. So in conclusion, I'll read this briefly and then we can finish up. This was a study of trace metal concentrations and bioavailability regionally and locally. We looked at zinc and cadmium sources, and we found that there's natural sources of metals that are much smaller than anthropogenic sources. Anthropogenic sources included shipyards, land reclamation, and fish farms. In terms of the ligands, the ligands for zinc is locally connected to regional and global distribution of ligands, so I'm pretty happy about that. There is this funneling effect along the Malacca Straits to Singapore to the south end of the South China Sea. there is a really large riverine influence, which we are really intended on continuing studying in the Rajang mostly, and in a couple of other places in Peninsular and Malaysia and Borneo as well. Cadmium is not too clear, so we really need to do a little bit more work on this. In terms of the time variability, the natural oscillations along the Malacca Straits, Singapore, South China Sea, can be related to the physical transport of the ligands along this transect. We're going to be a second time point now in the second part of 2017. We'll get a different time point so we can see about the monsoonal effect. But we're very excited about this coral project where we can look at longer time scales. And that's all I have to say. Thank you very much. It's been a fun ride.
I don't think there is time for questions. So we'll defer the questions at the final section, question and answer, where you all will sit on the couch. So you'll be comfortable. We should be here in a moment, and we have the next stop, Bio-Inspired Sensor and Robots by Professor Michael John.
Good afternoon. I came here this afternoon to review 10 years of exploring biomimetics to develop robots and sensors. A great many students, postdoc, and faculty are involved. I have marked the various developments by project, but just to give you an idea what I will cover today. In each case, it is emulating some outstanding performance from some living organism. So I'll talk, and we're going to have fun also looking at some of this through videos if the system collaborates. First of all, what is to learn about the fast starts of octopus? It's an animal that has no bones, it has no vertebrae, and yet it can achieve speeds and escape velocities like the vertebrate fish. So what are the mechanisms behind that? The second project I talk about is a robotic mure. Mures are birds that can fly like regular birds, but also they can dive underwater and swim like fish, long distances. And each medium has a difference in density of 1,000, and significant difference in speed and frequency of flapping. So how they can achieve with the same set of wings this, and what problems are set by that. If we had such robotic mures, we would be able to have a drone which will be able to track, for example, algal blooms, and then dive once it locates them, and underwater move slowly and make samples. There are several groups around the world that work on this problem, by the way. Then the problem of super maneuverability. Why can a dolphin and a sea lion be so maneuverable underwater, and underwater vehicles that we make have an order of magnitude less maneuverability? What we can do to cover that. Finally, a new frontier. We have underwater vehicles which are inspect, but they cannot do anything more than that, autonomous vehicles, that is. Why? Because they're small, and any force that they will apply will move them off the location they are. So they need to develop manipulators with very large forces in order to compensate for the unsteady torques developed. So how we can do that, and what examples we have. And then we will go to biomimetic sensors. I will cover them because this is a less structured area. You cannot do control unless you have sensors. So how can we do the same as fish do with the lateral line? That will be the main issue. And then we will have fun looking also at the whiskers of sea lions, which are an extremely interesting sensor. So let's start with biomimetic vehicles. Let's go first to an octopus. So what you see here is what looks like a bush. It's actually an octopus, camouflaged. They are masters at that. This is in continuous line. Once it's bothered by the diver, as you can see, produces some ink for camouflage, and then by the time you look again, the octopus has gone at least 20 or 30 body lengths. So it's an extremely fast maneuver, what it manages to do, this animal. It's propelled by ejecting water, so it's a jet-propelled type of device. But if you do the math, it turns out that the octopus maneuver is faster than a rocket with the same characteristics in space. In other words, in the absence of the surrounding fluid. That's a paradox, because we know that the fluid will produce some drag forces, and therefore it has to be less in terms of terminal speed than a rocket in space which has no such drag forces. So what is the mechanism that is behind that allows it to achieve higher terminal speed? Well, before I give you the explanation, we made a robotic device which could emulate this to show conclusively in an experiment that this can be done. So we made something that looks like a rocket, but has the shape of an octopus body when it's not inflated. And then we put a membrane around it. So you can see that on the left bottom. And then pumped water in it. So depending on the strength of the membrane, you have potential energy to consume in order to start. So what you see on the right is what happens once you let the fluid escape. So initially you have a relatively sluggish start in the first tenth of a second. By the way, this explains why the octopus needs the ink. The first tenth of a second or less than that, it's sluggish because it's a balloon, so it has a lot of added mass to start. So it needs to camouflage which way it's going to go because potentially the attacker would capture it at that moment. But then something miraculous happens. It accelerates, and as it deflates, it accelerates a lot faster than a rocket in space. What happens here? Well, the same added mass which initially delays the onset of the maneuver acts as a propellant. The added mass is like a mass. So if you take the derivative of the added mass times the velocity, you get the total force. So when the body has a fixed shape, the added mass is always reactive. It always opposes. But if the body deflates, the derivative of the added mass times the velocity gives you a propellant force, which is explaining exactly what is happening. So if you see the experiment, you can appreciate what I'm talking about. It's played. Do you see in the middle what happens? This burst of speed. And this is only limited by the strength of the membrane. If you can make a much stronger membrane and have initial potential flow, it will go a lot faster. So this property of the added mass of a body that undergoes shape change, or morphing as it's called, is a new mechanism which can be used to propel bodies. Now, it was interesting that when we did the experiments, we did them at Reynolds number roughly 700,000. That's a relatively high Reynolds number, because until then we were doing computational studies to predict what was happening. And it turns out that we were expecting a very mediocre performance on the basis of the simulations. But the experiment was much better. That's very unusual. So we sat down and studied what was the basic mechanism. So we came up with this number, which we dubbed the octopus number, since the octopus discovered it first. where it shows that this sigma star has to be above a critical level before you see the development of this propellant force. It's proportional to the square root of the Reynolds number, like many things with boundary layer theory do. Which means as you go up in Reynolds number, it's a lot easier to achieve this. So we went back and we corrected the theory, and indeed, it was the first time that I saw experiment of overcoming theory. So it was a very nice experience to go through, and now we're studying ways by which such body changes can be used for enhancing the performance. The second project that I will report is on the robotic mule, something that can fly and swim at the same time. So what's the basis of doing such thing? Well, in the process, we discovered why fish or swimmers like ourselves, or the turtle, which is in the middle row, or the birds, use a completely different stroke. So fish undulate their tails symmetrically, up and down. There's no difference in the up or the downstroke. Turtles, like when we swim as humans, use a stroke which starts up and forward and goes back and behind, like when we swim in a butterfly. Birds do exactly the opposite. They bring their wings back and up, and then down and forward. If you watch an eagle, some heavy bird, especially when they take off, you will be convinced that this is indeed the stroke. Well, it turns out that if you look at the wakes, each produces an appropriate force. In other words, fish have a wave-like passing through their bodies. So although they create unbalanced forces, they create lift force as well as thrust, which is the lift forces, and they don't care because they have a full wavelength, so the average lift force is practically zero. So they can afford to do this. That's why they have to have a wave passing through their bodies. They don't just flip just the tail. The turtle, which is the second in a row, have a rigid body. They cannot do such a wave like the fish. So because they're buoyant, any lift force would cause them to go up and down a lot. That's bad, like they would do for us. So by doing this inline motion, if you take on the lift force that develops, it's practically thrust, almost entirely. And, like you see here, the wake they produce, it's not like the fishes at all. The fish produce what is called a reverse Kármán street. The turtles produce pairs of vortices which are concentrated jets. There is no lift force involved. The momentum theorem would say that such a wake will not produce any of the kind. In contrast, the birds produce almost entirely lift, and this is reflected also in their wake, which looks like a starting vortex on each downstroke. Therefore, what do you need to do in order to produce something that flies and swims? Well, when it flies, it has to have a stroke like a bird, and when it swims, it has to have a stroke like a turtle. How about the frequency and the velocity? Well, it turns out that there is a non-dimensional number, the Strouhal frequency, which determines the optimal performance of fish and birds. And if you do the proper scaling, it turns out that it's indeed feasible to do this. So if you can watch here the video. You can see these birds which swim, which fly, and then they land, And they take a dive, and there they go. Do you see that they stroke like a turtle? They go back. They don't go the other way as they do when they fly. So the principle is simple. You just change the stroke angle. The question is, how do you do it with a robot? So you can see the device that Jakub Izraelovich at MIT has developed, which he tested under conditions of swimming underwater, which is next after this, and under conditions of flying in air. And he was able to develop the appropriate lift force and thrust. So he's in the final stages of explaining this. Moving to the third project, supermaneuverability. What do we need to do to make supermaneuverable? I'll go as far as I have. I don't want to go too fast. Thank you. So basically, when streamlined bodies maneuver, they generate these huge helical vortices, which is the source of slowing down. They slow down to half the speed at which they go. So what can you do? Well, you take lessons from reducing the bluff body drag, such as with controlling the flow with rotating cylinders, and you can achieve the same improvement in maneuvering. The high force authority vehicles, I will skip so I can have the time to talk about the biomimetic sensors. So fish have the lateral line through which they can have a three-dimensional image of their surroundings. With this, they can do the formation of fish. They can detect predators. So what are the basic developments here? First of all, these are the sensors through which fish sense the flow. They're like little pillars, about 1 millimeter in size. Why are they so small? Because the Reynolds number is less than 50 in terms of their existence, so they don't have a Karman street. So it's a good idea to replicate them, to have the same size. At the same time, they're embedded in a cupola, so it's a better idea also for us to embed them into a cupola. Indeed, you can have extreme sensitivity by doing this. So a whole bunch of such minute sensors were developed, so now we have the capability of detecting the flow around obstacles with very low power, inexpensive sensor arrays. The second project in terms of sensors was these whiskers of the seals, especially certain kinds of seals, the harbor seal and the elephant seal. If you look at the shape of these whiskers, they have a sinusoidal undulation. Nature doesn't make such elaborate things for fun. So it was important to test why they have this shape and also to explain why the seals are able to detect flows which are almost fossilized turbulence, down to 1 millimeter per second. You just put them in the flow, and if there is a wake, they will go and find the wake 30 seconds after something has passed. That's a lot of time for water. And it turns out that this undulatory shape has two properties. The first is that when they go forward in uniform water, there is no Karman street. So this could have very good applications in the offshore industry where they don't want the risers and the pipelines to shake. So they achieve this by having a wavelength to diameter ratio of about 5. If you do analysis, stability analysis of the flow, it turns out that that's exactly the optimum. So evolution works. The other property is that one side is flat, the other is narrow. So if there is any minute transverse flow, they start oscillating. And they lock in at the frequency of the oncoming wake. So they're the perfect sensor for detecting turbulent wakes. And not only to detect such wakes, but also to track them back and go all the way to the source. So MEMS and NEMS sensors, this is the skeleton of the head of a fish, which shows these openings through which fish detect pressure. So we were able to emulate the same sensors that the fish use. So I'll flip through some of the slides. I will show you some of the tests which show that these sensors in the field apply to kayaks and underwater vehicles. This is the size. You can see the Singaporean coin here to give you an idea of the size of all these sensors. So there's a whole array of such sensors that were applied, and unusual things like crocodile-inspired. Crocodiles have these dome-like sensors through which they have directional sensing of pressure. These are the seal whiskers. You can see the undulatory shape, which is flat in one dimension and much wider in the other. And this was the hydrodynamic explanation of the sensitivity, which was the major development of this project. Finally, chemical sensors were developed based on the sharp olfactory system, which have the shape and the form of the animal sensors. So necessarily, this is just a sample of what has happened, but I tried to spend a little more time in some of these projects just to give you an idea of the principles and the conditions that allow this performance. Thank you.
Exactly. Thank you very much. This was indeed fascinating, and too bad that we had to rush Michael a little bit, because there was lots of stuff to be told. It's time for our star, the bright star of Sensam, Shakil Rehman. So Shakil will talk about optics underwater when there's lots of particles. How do you see through particles? And we will leave the questions for Michael's talk to the panel, which will be later. Okay.
Hello. As I have been introduced quite nicely, thank you very much. So my talk is a little bit shift from regular Sensam modeling and sensing methods, but still it has quite relevance to sensing problems. For example, today I will talk about basically imaging or sensing through highly scattering media, such as turbid water and or polluted gases, for example, pollution. So, okay, so what we do is, so why is this scattering is a challenging problem, seeing through dense media? So as we know, so light can be used as non-destructive and non-invasive tool, as opposed to any other existing mode of imaging. For example, through the whole spectrum of electromagnetic radiations, light has this ability to give us these two very good properties, that it does not destroy or disturb the natural state of the biological cell, for example, biological tissues, or even other non-biological samples. So here I will talk about few examples which we have worked on and in Sensem projects. So a little bit of a background, why is it so hard to see through very highly turbid medium, is that it's absorption and scattering of light when we try to use to do imaging. So a basic background is that light, when it scatters from, let's say, some gas particles or particles, so it can scatter in few different ways. For example, if light interacts with the particles and scatters without changing its color, for example, we call it elastic scattering on this side, as you say. So a good example of this elastic scattering is the Rayleigh scattering, which is the color of sky, which is blue sun rays scattering from the sky and giving off blue tinge to our atmosphere. So this is Rayleigh scattering. Another example of Rayleigh scattering is example of elastic scattering is the fog, for example, where the modeling is done by Mie scattering, we call. And again, here the wavelength of light doesn't change, but depending on the size of the particle, light direction scatters more for small particles and less with larger particles. So there are other nonlinear methods of scattering as well, Raman scattering, Brillouin scattering, but we don't use them in our Sensem case. But in my background actually is also using all of these modes for imaging biological tissue, which I have done in my earlier stints. So, so for imaging particles, people have used a plethora of modes. Some of them are here, from classical sieving like grandmother's style to using highly sophisticated methods of laser diffraction, sedimentation, I don't know what this is, and the dynamic light scattering. Well, I know, but yeah, all of these methods. All these methods have been are used in industry. They have their own niche applications where people can count particles using a microscope, for example, or dynamic light scattering. We use diffusivity of particles, which gives the size and number of particles. And of course, you can image a particle or gases, for larger particles, and then count them. Aerosol mass spectroscopy can be used as well. So here, our solution to add on to this was using a technique called digital holography, which can simultaneously give size, shape, and number of particles from images. So all of these methods give one property at a time, which they are optimized. So digital holography has this ability to give us all of these parameters simultaneously. So a little bit of background on what digital holography is. I always show this plot. So it's a good way to visualize that any object we see can be expressed as in some kind of form of mathematical way as this amplitude and phase. So when we detect this light scattering from an object, so what we do is we take its amplitude, and all our sensors and our eye, for example, our retina and photographic films or camera sensors, they respond to this amplitude variations of the light, not to the phase. Phase is the temporal variation of the light or electromagnetic field. So what happens is, in doing so, seeing, detection, or recording, we lose this phase information. So phase is very important. It tells us where the light is coming from. For example, if you look at this position, light from 2 point sources, when it travels to different distances, you can see that the curvature of the field is changing. So that change of the curve is what we call phase front. And a standard way of imaging loses that information. So interferometry and some other methods like holography can be used to actually get that phase information. The method is very simple. All you do is you take the object wave as well and add it with a reference wave, a background, for example, and do this little simple mathematics, and then you see what happens. You get 4 terms, and you see these object term is present here with amplitude and phase encoded in itself. So here, if somehow we can get this term out of the recorded material, then we can get the object information. So that's what we do. So what we do is we record a photographic-like image, but we call it a hologram. So where scattering medium or particle is illuminated with a coherent wave like a laser, and an image is recorded on a camera sensor. So and then we get the phase information. So why phase? Because phase gives you the temporal information of the field, and from there I can tell not only where the light was coming from, but also I can get the size information of an object if it's a bigger enough or a larger particle. So we use digital holography in our Sensem project. For example, this one is looking at particles or in this case bubbles, for example. So this is not this one. So here what we do is we record a hologram. As I was telling you, this is a single frame of a hologram of particles falling into a test tank. And so each frame has been reconstructed into this 3D position and distribution of particles. The color coding is the size of the particles. And then also we can quantitatively measure the size distribution, from a few microns to even up to millimeter range. So the setup we use are pretty simple. We use a laser sample holder and a camera, and then we use computer codes to reconstruct. That's fine. So another example is we again record holograms of what we call nanomotors. So this work is done with the Miaz group at NTU. So they make these gold, nickel, platinum composite, what they call nanomotors, and they when they put them in hydrogen peroxide, they start moving through this catalytic reaction. So they move very fast. As you can see, these are here they are. I think this is not really working, but they move very fast. So we want to quantify the motion of these particles. Oh, by the way, these are not, you cannot see the motor. They are too small for these images. So what you should see is the bubbles they create on the surface of the, so bubbles grow and collapse, and then they move. So maybe I can show you in the next slide. So here is this is the model we tried to explain, that this is this gold, nickel and platinum composite material nanoparticle, and it creates this bubble. As the bubble grows, it pushes the motor in forward direction, and then it collapses at certain distance, let's say here. And then, so this is the dynamics, we say the bubble size growth and collapse of the bubble. And in our hologram, we can image that, and then from this hologram, we can 3D localize this bubbles, various sizes and positions. And from here, we can tell the parameters like speed and of course the size distribution of the bubble in this case, but we are more interested in the dynamics of the motor in this case. Another example which we have worked on is the hyperspectral camera development, which we developed in this in our project, again with the Miaz group. So hyperspectral imaging is based on recording a 2D image with the third dimension, where the color or the spectrum is coded into at each pixel. So basically, a grating is used to disperse the light, and then and then the image is recorded either by scanning onto the scene or recording on a 2D camera. So classically, this has been done, for example, through satellite or airborne imaging devices with scanning methods. But we have developed a method in which we can use a two-dimensional image and another technique, what we call a rotating grating, for example. Instead of recording one image at one position of the dispersing medium, we rotate the grating at different angles and record multiple images. And a micro lens array is used to mix the data. So essentially what we get is a blurred image of the scene, and then we have written efficient codes to get the information out of it. So here is a lab model of the camera which we worked on, and this camera has now been developed. It's a prototype, and it's now in the testing phase. So the advantages are high light efficiency and fast measurement and miniaturization. So the final application which we started for is this to be deployed in a microsatellite, but the same camera can be used for example, from an airborne system for algal bloom detection and vegetation monitoring probably is the best application we can think of. So this is another example of how do you get the spectral information and concentration maps for such a camera. Finally, I will just mention another work which based on, again, a sensing and imaging method, but it's based on rigorous calculations of light scattering and propagating from scattering media to a sensor, for example. So, so here we model, solve exactly the light distribution within the particles and its transport from the particles to let's say a sensor. And if in doing so, if you see this, this is the calculated hologram of this model, and this exactly matches with the real hologram. So now, so why we do that? Then what we can say is we can propagate back with the same our models and get the information about the particles, like their refractive index, maybe size, and then also other parameters. So if once we perfect this model, we can record holograms of an unknown sample distribution and use our rigorous models to find out the physical properties of the scattering media. So these last example, maybe if I have time, I can say is that is a thing called resonant light scattering from particles for environmental sensing applications. So here we use a thing called whispering gallery mode. So think of a circular particle, for example, and if you shine light in it, light leaks into the particle and then gets trapped. So that trapped light can be used in a sensor like here. Suppose I have this capillary tube, for example, and a gas, for example, is flown into the tube, and I excite with a laser light these we call whispering gallery modes, and then and detect the light at the other end of the fiber. So what we get is a graph like this, where the spectrum of the resonant modes is detected. Now, if there is a particle disturbing the mode structure in the of these whispering gallery modes, the spectrum will change. Either this peak will shift, or its width would change. So that change of width or the spectral shift would give us physical properties of the gas particles, for example, or fluid flows. Temperature and refractive index like parameters can also be detected. Yeah, so this work is being done by Xuan, who is mostly a theoretical modeling guy and quite good at it. Yep, thank you.
Oh, no, no.
I wanted to do
Can you hear me now? Yes. I wanted June to talk because June is one example of a success story in SENSAM. In fact, his picture was in the picture which Andrew showed of the graduates who have gone on to a successful career in universities. June came with me as a postdoc beginning of 2009, basically at the beginning of SENSAM. At that time, we were working completely in different things, and in fact, he was working on data simulation, and the first work we did was to assimilate in a model of the circulation in a channel of Singapore, the data collected by Professor Patrikhalakis and his group. So we have papers going back to that work. Then June became a visiting scientist, and I think 3 years ago he went to Beijing University, where now assistant professor on the way to possible next coming tenure process. So I want also to say a few words about my two phases in SENSAM. During the first 5 years, I studied with various postdocs and collaborators, a lot of collaboration, for instance, with the people from NUS, National Dr. Pavel Tkalic, and we studied the various oceanographic aspects of the South China Sea. Dr. Haoliang Chen, who is here even though he has also gone to another job. We studied the general circulation of the South China Sea, properties, temperature, water mass properties in the Malacca Strait, basically storm surges of the South China Sea, which is a problem which affected Singapore in the past. Those were mostly and predominantly oceanographic studies. During the second phase of SENSAM, I shifted gear and I started a wonderful collaboration with the Professor Fatih El-Tahir, whom I don't see here. Well, in any case, and we've started this collaboration in which Professor El-Tahir, Marine Regional Climate Model, which is an atmospheric model, and my model for the ocean, which is a FVCOM, Finite Coastal Ocean Model, were coupled using a number of joint postdocs, and the first postdoc in this couple work was again Jun Wei, and then we had other postdocs, Peng Fei Xue, who is now professor at Michigan Technical University, and then the last one is Dr. Yunfang Song, and he's doing another couple modeling simulation. So in these last 5 years, I have focused on the climate research using coupled climate regional model, coupling Professor El-Tahir atmospheric model and my ocean model. June is going to talk now about the coupled work with a previous version of the coupled model, which now Yunfang has modified, and he's going to focus on large-scale properties, oceanographic properties of the South China Sea, especially trying to determine the influence of the large-scale circulation from the Pacific Ocean in different regions of the South China Sea, what we call the oceanographic bridge or the atmospheric bridge. The model being coupled can simulate the atmospheric circulation, for which a region, as June will show, a region of the South China Sea is modified in temperature and circulation by the atmospheric bridge that is the effect of the atmosphere from the Pacific Ocean to the South China Sea. The northern part is affected by the oceanic bridge, which is the big inflow through the Luzon Strait, and the last part, the shelf, Sunda Shelf, is affected locally by the local heat fluxes. So this coupled work reflects also large-scale properties of the Pacific circulation, into which basically the South China Sea is embedded, and he has studied from the seasonal variability to the interannual variability and the decadal variability. So he's going to talk about these variabilities of the large-scale circulation.
Okay.
Okay. Yes. No,
Can you
no, no.
hear?
He has to
Okay,
do
thanks
that.
for Paula for. Okay, I used it. Okay, thanks Paula for the kind and detailed introduction on how I grew up and from one of her kids to now a professor in Peking University. So after 2011, I went back to China. So I have been continuing my collaboration with Paula and Fatih's group. So today I'm going a very short story about variability and regional climate in the South China Sea. First of all, I would like to show you the global climate variability, starting from the 1880s to the present. So we can see the global mean surface temperature is quite stable in the early 19th centuries. So it underwent the first global warming around the 1940s and dropped down quickly and became flat until 1980s. And it goes another global warming from 1980s to 2000 and turns flat again. So some people call this global warming hiatus, but unfortunately, in 2015 or 16, the temperature goes up again. So, we can see that every time the temperature goes to a rapid global warming, it always has a so-called hiatus period before the rapid warming. So in this study, we've focused on this part from 1970s to 2000 because we don't have too much data in the very old time to drive our model. So in this period, we try to understand how the regional climate variability in the South China Sea in response to this global forcing. This is the South China Sea. So this is South China Sea. It is almost closed with a big Luzon Strait connecting to the Western Pacific, another strait in the Kalimantan Strait connecting to the Java Sea. So the climate in the South China Sea can be driven by local forcing or the remote forcing. For example, the ENSO can propagate westward with the North Equatorial Current and then Kuroshio, and then goes into the northern South China Sea with the Luzon Strait. On the other side, it goes into the Java Sea with the Madanao Current and ITF. On the other hand, it also can affect the South China Sea by atmospheric bridge. So this is for the normal year. So this is Walker circulation and the surface trade wind towards the maritime continent. And for the El Nino year, so the equatorial Pacific warms up, it increased the convection and this kind of secondary circulation. So this circulation will decelerate the trade wind in the western part of Pacific and also the South China Sea as well. So in this study, we're trying to understand how the regional climate variability in the South China Sea is driven by locally or by the remote forcing. If it is by remote forcing, how it goes with the oceanic bridge or the atmospheric bridge. So to answer this question, we need a couple model. So for the atmosphere model, we use a regional climate model, which was developed by Professor El Tahir's group. So later they upgrade to a newer version called MRCM for many studies, which I didn't list the publication in here. For the ocean model, we use FECON and the maritime continent. This was developed by the Professor Rizzoli's group. So the ocean-only model we have been used for many studies since 2011 to the present under the Sensen program. So I built a couple model called RICM3 and FECON. So yes, I am the coupler of the two groups. So this couple model has 5 kilometer resolution inside the South China Sea and 200 kilometer along the open boundary condition. So we have been used this couple model for air-sea interaction and also the regional climate variability from seasonal to interannual and decadal time scales. So this is how I build the couple model. So the atmosphere model called SST from the ocean model and send the wind stress and heat fluxes back to the ocean model. We also examine the two types of feedbacks. So between the SST and the heat fluxes, there is a negative feedback. So which means the SST goes up and it generates more clouds and the heat flux goes down. So another one is between the wind evaporation SST. The feedback is positive. that's the method to separating the oceanic and atmospheric forcing. Well, actually, this is temperature equation and momentum equation, so we can imagine. Okay. So SST changes is equal to the advection and the missing and the heat fluxes. Kinetic energy equals to advection and pressure gradient and wind stress. So obviously for the South China Sea, the advection is obviously through the Luzon Strait. So we call that oceanic forcing. And the wind and the heat fluxes are obviously the atmospheric forcing. So the method is trying to separate this total SST change to these two terms. So this term is missing, and this is a pressure gradient. And later I will show you these two terms are not important. So this is the model configuration. So see if we can follow this methodology. So we run the fully coupled model for 70s, 80s, and 90s as a control arm. And we have another called partially coupled model for 80s and 90s, but we fix the boundary condition, lateral boundary condition as 70s. Remember, in the first slide, the temperature in 70s almost flat. So we use that as a reference to see the global South China Sea warming in the 80s and 90s. So the third one is also the partially coupled model. So we fix the surface heat fluxes and wind forcing as the 70s. And then we can calculate the warming by the difference of the SST in 80s and 90s minus 70s. And we also can calculate the difference between experiment 1 and experiment 2. That's the SST due to the boundary condition. And also the difference between experiment 1 and 3, that's the SST due to the surface heat fluxes. See if we can follow this. I repeat again. And experiment 2, we fix the boundary condition. So the difference between the fully coupled and the partially coupled is the component due to the boundary condition. We fix the surface fluxes, so the difference stands for the SST changes due to the surface flux. So by doing so, we can decompose this SST into these two terms. Okay, this is the result in the South China Sea. The previous ones for global. So the black one is the solar reanalysis data. So red one is our model. So our couple model can capture the data as very well. And this is the total SST change. Actually, it's warming in the South China Sea. So this comes from our model, the left one, and the right one comes from the SODA. So basically, they are similar. So we can recognize three regions in the South China Sea. The northern South China Sea, region A, it has a very little warming, so it's close to zero, and obviously is affected by the advection through the Luzon Strait. In the middle South China Sea, the region B, that has a maximum warming up to the 0.4 degree, and the region C is in between. So we can decompose these total SST changes into these two components, the one due to the boundary condition and the one due to the surface heat fluxes. So we can see roughly the total one equals to the summation of these two components. So we can also see this time series, so which means that the SST changes is roughly equal to this plus that, and the missing term is not important because in the ocean upper layer, the SST is well missed, so the missing term doesn't contribute to the SST change. And also we can see the three regions get into these two components. Region A is here, B is here, and C is there. So we can see that region A is dominated by the advection through the Luzon Strait inflow, and the region B and region C are far from the Luzon Strait, and thus it was affected by the atmospheric forcing. But the question is this forcing local or remote? That's the question we want to answer. So then we calculate the correlation coefficient between the SST component with the heat fluxes and wind speed and the ENSO signal. So the result turns out that for SST variability in the region A, the ENSO signal can go into the northern South China Sea through the Luzon Strait. That means in the El Nino year, more cold water get into the South China Sea, so SST going down. So we see negative correlations. So for the region B, the ENSO can affect SST through the trade wind. Remember, in the previous I mentioned, in the El Nino year, the trade wind was weakened. The evaporation was weakened as well. So SST going up, so we got the positive correlation. So the opposite sign of these two correlation indicate that it must be driven by different mechanisms. One is going through the oceanic bridge here, and the other way is going the atmospheric bridge. For the region C, so it is basically driven by the local heat fluxes with a very high correlation in the two components. So we also did the circulation in the South China Sea, the same thing. So the total one, the total one can decompose into the two components. So we can see the surface kinetic energy is basically identical to the boundary condition. It shows clearly South China Sea through flow. This is for the barotropic one, even the same. So the atmosphere forcing on the circulation is one order of magnitude smaller than that of ocean boundary condition. So that means ocean boundary condition dominate the South China Sea through flow. So so this is the same. So that shows the middle part. You can imagine the pressure gradient is not important because the South China Sea flow is basically on the geostrophic balance. So we check the South China Sea through flow in the El Nino year and the La Nina year. So for El Nino year, the South China Sea through flow is getting stronger. It brings more cold water into the northern South China Sea. And this is the anomaly, so it doesn't mean going back, it means it's getting weaker. So it less water get into the South China Sea. So summary, so in this study, we based on a set of experiments, we can decompose the global forcing into oceanic forcing and the atmospheric forcing. So we find out that the global signal can get into the South China Sea through two bridges. So our conclusion is that the northern South China Sea is affected by the oceanic bridge. So the central South China Sea is affected by remote forcing as well, but through the trade wind. That's the atmospheric bridge. And the shallow Shunda Shelf in the southern China Sea is basically driven the heat flux and SST interactions. And the circulation in the South China Sea is simple. It is dominated by the Luzon Strait inflow. That's the oceanic bridges too. So that's my story. Thanks for listening.
Thank you very much. Yeah. So now we're going to invite all the speakers of this session to take a seat. And then we're going to do some questions and answers. So the topics that we have covered so far are very diverse, ranging from heavy metal, not music, but the other stuff. Everything is correlated with everything, but the question is how you make that bridge. Yeah.
Through the atmosphere or the ocean?
Exactly. It's a coupled system. So, the floor is open for questions. And if you want to ask a question, raise your hand, and then somebody will come over and bring a mic. It's always too many at the same time. What about you? Why don't you ask a question? Huh? No? Oh.
scale circulation, because even though you look at paleoclimate, they were measuring all the corals also up to now. Can you distinguish in your coral measurements El Niño years, La Niña years, normal years, looking at basically the present measurements in the corals to see how they reflect the larger scale circulation? I had a wonderful conversation, I don't think she's here now. She's a student, oh yes, yesterday, and she's looking at corals which are very near the surface in the Makassar Strait. And she finds a fantastic story of correlation through the Makassar through flow, which is the Sibutu Strait coming down Makassar, or the other one, which is the South China Sea through flow coming from Luzon. So I was wondering if you can correlate your measurements. They are not surface, her corals come to the surface, but if you can really make a similar story, distinguish between El Niño, La Niña years and normal years.
Okay, I'm not going to be able to answer for the tuna coral, although Intan probably could answer the question if she were here. But it depends very much on the sighting of the coral and what you're going to see. In some areas, if you have a strong sea surface temperature signal, you'll see that. But in other areas, you'll see it in the rainfall, and then it'll come out in the salinity signal. So it very much depends on the sighting of the coral relative to the ENSO process. The tuna is not really in an area which is going to be directly showing warming due to ENSO or salinity due to rainfall from ENSO. So I'm not sure that it would show that signal. But again,
What is your coral? What are your corals? The location of your coral site?
The southern Makassar Strait. So just east of the Java Sea, in that southern portion.
It is inside Makassar Strait, on the left side in shallow water.
Yeah,
It is in Makassar on the left side in shallow water.
yeah. So you have the seasonal South China Sea influence coming from this really shallow Java Sea, and then you have the Indonesian through flow going through the Makassar Strait.
No, I understand. Your location is totally different. I understand. Because again, yesterday we were talking and we are thinking with June to modify our grid in such a way as to resolve much better the little strait like Sibuto, which come from Luzon and go down to Makassar.
Actually, I have a question for Ed. So I remember in your talk, the record for SST record from 1920. Is the location actually is between my region B and region C, somewhere and south of the Vietnam, right? So you are linked that to the ITF, so stronger ITF and the weaker ITF. So according to my understanding, ITF doesn't go into the South China Sea, so that should be the South China Sea true flow, and not the Indonesia true flow. Is that correct?
but the plot showed for those few years where they had the data, there was a correlation between the density in the South China Sea and the strength of Indonesian through flow, even though at Natuna, it's not the Indonesian through flow that you're seeing. So now whether we can come up with a mechanism that would account for that correlation or not depends on whether you'd want to believe it in the longer term.
Okay, so we cleared that. We have more questions from the audience. Oh, Leslie.
I can show.
Okay.
Michael, you were cut off, ran out of time when you were talking about chemical sensors, and I thought you were saying something that the geometry, the shape of them mattered. For chemical sensors, is it purely the chemistry, or are you trying to? Where's the biomimicry involved in the chemical sensing? I guess is the question.
Yeah, the biomimicry in this particular sensor, because there were some other sensors which we're talking about, was trying to emulate the ability of sharks to detect very small parts of blood, for example, in the water. And it's a matter of concentrating a lot of fluid passing through a relatively small area. So the lamella of the shark and the equivalent biomimetic. We had all these little pillars on which, through microfluidics, basically it's forcing a lot of flow through this, and that makes it possible to detect very small traces of the material. So that was the biomimetic in this particular part. It was not on the function of the sensor itself, but in terms of the microfluidics.
Hi, I have a question for Michael as well. So it's always so fascinating to hear you talk with all these great soft robots and biomimetic sensors. And I was wondering, with all this technology that you've developed, could you comment on kind of the application space for that and how that's evolved over the time in Sensam or beyond?
Sure, the easiest application is in terms of the sensors, because we used these sensors in the field. So we used the whisker sensors, we used the flow detecting both velocity and pressure. So for example, we put it in small AUV, so if there is a side current, the AUV can detect there is a side current, and instead of trying to fight the current and spend its battery, it's doing what is the equivalent of tacking in a sailboat. And you can save a lot of energy by doing that, so you don't get all the cross-flow drag. So the sensors are the easiest to apply. In terms of the robotics, of the biomimetic robotics, it's still in the development, but you get principles to apply. For example, the use of fins by vehicles. It's something that actually now we are implementing, because the fins are controllable. So if you watch a tuna, or better a sailfish, they have these huge fins which are they employ. This changed what's called the aerodynamic center, which is a very important property of streamlined bodies, because those determine maneuverability. And if you open the fins and close them, what you do essentially, you instantaneously impose an unstable body which turns a lot faster, and then you stabilize it. So this morphing of wings is the first fruit of all this effort, which will allow vehicles to turn very quickly. So it's coming along, but it's still, we need materials, flexible materials, which will be able to implement this flexibility of the fish. So we're going closer to that. But the concepts, how they get applied, they may not look at all like fish do or anything. You learn and you do different things. For example, the octopus, we are not going to make vehicles which swell and expel, but there are other things that we can do to increase temporarily one part of the wing, for example, and then quickly retract it.
Thank you, Michael. I think there's a question in the back.
Okay, Ed and Junvei, a question for the two of you. I'm wondering about other extreme meteorological events, such as years that maybe have considerably more typhoon activity. Or you both talked about El Nino and La Nina, but the other dynamical conditions that set off the large-scale changes in the interannual variability of the monsoons or of the hurricanes through the areas. Have either of you seen any of these types of signals in the two different approaches that you take?
I can be quick. I haven't searched for that, so the answer is I don't know.
This is a climate model, so the time scale is up to the seasonal. So we didn't look at the weather scale. No.
The question go for Gonzalo. Gonzalo, you have conducted a lot of field work in the region, and that represents a big effort, a big coordination, and a lot of collaborations with the people in the region. I'm wondering if you could elaborate a little bit more on your experience.
Wow, that's an interesting question. Yes, I mean, pretty much things started slow. I mean, initially I had to get all the permits and all the things to get things up and running here in Singapore. And then I basically lucked out with Moritz and Asani and Yanni and then Jenny, and then a lot of people ended up. I mean, Malaysia in general terms is a small ecosystem. So you know one person and everybody knows everybody else. And then I basically lucked out with a couple of friends who opened up to a lot of other friends, and then soon enough we were all happy about sharing boats and doing things together. Because, I mean, the truth of the matter, I mean, the naked truth is that Malaysia doesn't have a lot of money, right? And Singapore does. So there's a lot of things that we can do that they cannot, and there's a lot of things that they can do that we cannot. So we help together, and in a team effort, it gets done. It took some time at the beginning, but after we made friends, we were just super happy to work together. Yeah. Thanks.
This is a question, I'm going back with my memory. In one of your past presentations, I remember you talking about mimicking the gills of a fish. And the gills of a fish and the mechanism with which the fish breathes, so to speak. Am I wrong? Because I remember you showing the gills of a fish and trying to mimic the behavior.
No, I haven't talked about that.
Not now. Oh well, maybe there was your sosia. Your
It could very well be one of the students that was talking about that. Yes.
Okay, well, obviously, I'm talking about my memory is failing. Never mind. Sorry about that.
Sorry, I would like to ask Gonzalo a question. Hello? Yes. I was quite excited to see your zinc data. It's the first time I've seen it, and then the Rajang is extremely exciting for me, for our work. I was wondering if it's due to the amount of organic matter that's coming out of the river, or is it an anthropogenic source, or do you have any input on that? Because we have all this organic matter coming out. We think it's the largest source of organic matter to the South China Sea ever measured so far. Mm-hmm. So is it due to just the sheer amount, or is it due to the deforestation, oil palm plantations, and so on? So,
well, you know, the Rajang and all those rivers in Borneo are basically like an open question, right? I mean, we can look up some things and on Google Maps, and then we go and we find something that is completely different, right? One. And then two, as you start to go up and down through the salinity gradient, there were a couple of places that it wasn't just simply organic matter from the river itself, you know, sort of diluting down, or at some point precipitating out, and just a little portion, so surviving the salinity gradient and going out. There were a couple of things that were a little bit confusing. So I am really looking forward to getting my paws into more of those samples later, to basically to answer these questions. Yeah.
Thank you.
Okay, so I think this is a good time to thank the speakers again. And it has been a very interesting mixture of topics, which is kind of reflecting the interdisciplinary character of environmental science. So let's continue the discussion over a cocktail and thank the speakers. Thank you very much.